Okay, still here. So where we left off was dipole moment. And we need to talk about dipole moment because that is actually related to polarity of bonds. Dipole moment is something that results from, basically it's like a degree of polarity of a bond. It results from the separation of positive and negative charges, and the magnitude is just QR. This would be for the separation of two charges of equal magnitude, whoops, but opposite sign by a distance of r. And just a quick example of that. The dipole moment for separation of a proton and electron would be mu is equal to, this is, oh, by the way, this is, remember, this is the Greek letter mu. We last saw it as an abbreviation for micro in the metric system, and they've decided to use it again here because I guess it's probably supposed to stand for moment. They needed another M, and so they reused it here. They figured, oh, there's enough of a difference between metric units and symbol for something you'd calculate that they could use it again without too much confusion. Anyway, mu would be equal to the charge on a proton or electron, which are equal, and we usually think of a charge on a proton or an electron as being +1 or -1, but that's really for convenience. The SI unit for electrical charge is known as the coulomb, and one proton or one electron would have a charge of 1.6 times 10 to the -19 in units of coulombs. The distance by which they are typically separated would be 130 picometers. And that's 130 picometers is 130 times 10 to the -12 meters. And when you multiply those together, you get 2.1 times 10 to the -29 coulomb meters. And a coulomb meter is known as a debye, because debye is the name of one of the scientists who pioneered research into this area. Or sorry, not a coulomb meter, but anyway, we usually convert to debyes. And one debye is 3.34 times 10 to the -30 coulomb meters. So this is 6.2 debyes. This is actually kind of an idealized situation because this is, sorry, excuse me. This is actually more polar than a pure ionic bond with that bond length would be. The dipole moment of a pure ionic bond with a bond length the same as this would be about 6 debye. And smaller charges and smaller separations generally lead to smaller values for the dipole moment. And since we're dealing mostly with covalent bonds here, you would expect the dipole moment to be less than the value for an ionic bond. So in units of debyes, it should be less than 6. And this basically tells you to what degree the electron is transferred, as opposed to being shared. this basically the dipole moment of a typical ionic bond would indicate that the electron is being transferred. Something less than that would indicate that it's being shared to some degree. But basically, the lower the number is for the dipole moment, the more or more equally the electron is being shared. Similar concept, trying to tell how much the electron is being shared versus transferred would be percent ionic character. And that's just the measured dipole moment of the bond over the dipole moment if the electron is completely transferred. Times 100 because it's a percentage. And generally, generally bonds with more than 50% ionic character are called ionic. And if it's less than 50% ionic character, then it would be covalent. If it's essentially fully or a nonpolar covalent bond, then that would essentially mean 0% ionic character. Okay, so what we're building up to here is being able to write Lewis structures for molecules and polyatomic ions. And a polyatomic ion, if you recall, is basically a molecule with a charge on it. Okay, so molecules and polyatomic ions. So how would you do that? Well, we've seen a few simple examples so far, like Cl2 or H2O, and in those, it's pretty obvious how you can piece the atoms together to get octets or duets on the atoms that want them. But there are a lot of larger molecules where it's not quite so easy to do. And so there is a certain step, certain procedure, certain sequence of steps that if you follow them, you should get a good Lewis structure for the molecule, even in cases where it might be possible to come up with more than one plausible Lewis structure for a molecule. And actually, there are quite a few cases like that. And so following this sequence of steps will help you avoid mistakes and will help you sort of get things the right way around. Okay, generally, well, actually, most books, including the one we're using, tend to use the terms interchangeably, but technically Lewis symbols are the symbols for individual atoms, with the requisite number of dots around them representing valence electrons, whereas Lewis structures are what you get when you put those Lewis symbols together to form a structure, or basically like a big Lewis symbol for an atom, or for rather a molecule. So we're doing Lewis structures now. And Lewis structures offer information on bonding. They don't show us directly what the molecule looks like. Sometimes the Lewis structure comes out looking like what the molecule really looks like, and sometimes it doesn't. When it does come out looking like what the molecule really looks like, it's just sheer luck, just coincidence, really. But what Lewis structures do is they give us information on the bonding, that is, what is bonded to what and how. And that gives us the information to determine what the molecule's shape is. And it's knowing that knowing the shape of the molecule is actually a very important thing to know. But Lewis structures don't give it to us directly. Lewis structures give us the information to find out what the shape is. So they give us information on bonding, and we can use that information to find out what the shape of the molecule is. So the steps, if you follow these steps in order, you should be okay, at least with anything that we encounter in this class. First of all, arrange the atoms in the correct skeletal structure. That's the correct relative positions. So again, this is the skeletal structure. Most of the compounds or molecules or polyatomic ions that we will encounter in terms of Lewis structures will take the form of a central atom surrounded by other atoms. Sort of like CH4 with carbon in the center surrounded by hydrogens. And so your main task here in step one is to determine which atom is in the center and which atoms are around the outside. The central atom is usually the least electronegative element present. Or the unique element. That is the element that you've only got one of. But no matter what, it's never going to be hydrogen. Doesn't matter if it, even if hydrogen is the least electronegative element and the unique element at the same time, hydrogen cannot be at the middle of anything because hydrogen can only form one bond. And in order to be in the middle of something, you have to have something on at least two sides. So hydrogen would have to form at least two bonds, and it can't. So hydrogen can never be in the middle of anything. Hydrogen is always what they call a terminal atom. It's always around the outside. Okay, so one bond means never in the middle. Two, once you've decided which atom goes, and of these two things, sometimes it's the case that the least electronegative element is also the unique element. Of the two, though, if they conflict, the second one actually prevails more often. That is, the unique element ends up being in the middle. All right, number two is about find the total number of valence electrons in the structure. Okay, so that means add up valence electrons for all of the atoms of all of the elements in the formula. Okay, so you do that. If there is a charge on the structure, so in other words, if it's a polyatomic ion, you add 1 electron for each negative charge. So if it has a -2 charge overall, you'd add 2 electrons to the total. And you would subtract 1 electron for each positive charge. Yeah, because that's how you get a positive charge, by losing valence electrons. And so if it has a +2 charge, you'd subtract 2 electrons from the total. Then you can connect the central atom with the outer atoms with single bonds. For now, that's 2 electrons each. That doesn't mean you're necessarily going to end up with single bonds at the, once things are said and done, but you can start out with single bonds and go up from there if you need to. Step 3. You complete octets on the outer atoms, except hydrogen. Hydrogen does not want an octet, and hydrogen will always be an outside atom. If any electrons are left over at this point from the total, you're comparing the number of electrons you've used versus the total number of electrons in the structure. And if you get to this point and there are any left over, you place them on the central atom as lone pairs. Okay. And number 5, check for octets. And if any atom that wants an octet, keep in mind there are certain elements like, say, aluminum and boron that can be stable with less than an octet of electrons around them. But if it's an element that wants an octet and it doesn't have an octet, then you might have to try double or triple bonds. By looking to one of the atoms that's bonded to the one that's lacking an octet and making that atom share one of its lone pair electrons in a bond with the atom that's lacking an octet. Probably the best way to submit these rules is to go over some examples. So first, I'll try an easy one. Carbon tetrachloride, CCl4. The first thing you want to do is decide, relatively speaking, where these atoms go. And there's only one carbon and there are 4 chlorines Also, carbon has lower electronegativity than chlorine. So both of those factors tell us that carbon is going to be in the center. And for the Lewis structure, the exact arrangement of the atoms doesn't really matter as long as you get the right thing in the center and the right things around the outside. But I'm going to space the chlorines, more or less evenly around the carbon just to make it look nice. So there is your skeletal structure. Then we need to find the total number of valence electrons. Okay. Valence electrons. Carbon has 4 valence electrons. Each chlorine has 7, but there are 4 of them. And when you add all of that up, we have 7 times 4, which is 28, plus 4. We get 32 valence electrons for this entire structure. Okay, so we have 32 electrons to deal with here. There's no charge on it, so we don't have to add or subtract any. And we start out connecting the inner atom, the central atom, to the outer atoms with single bonds. Remember though, each of these bonds is 2 electrons each. So we've used 2, 4, 6, 8 so far. The next step would be to complete octets around the outer atoms, and chlorine does want an octet. So keeping in mind that we've used 8 electrons already, we can start adding octets, making sure that we don't go over the total. So we've used 8. So here's 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. 32. Okay, we're done with the total. We've used 32 electrons. We can check for octets in this structure. We can check chlorine, and we see that chlorine has 1, 2, 3, 4, 5, 6, 7, 8 to 2 in the bond. So chlorine has 8. We could check the other chlorines too, but all the chlorines are the same in this molecule. So, you can do it just to be sure, but they're all going to come out the same. Try the carbon. Each bond is 2 electrons, so carbon has 2, 4, 6, 8. Carbon has 8 also. And so everybody's satisfied. And we're done with our Lewis structure. That is the Lewis structure for CCl4. You can erase the circles if you want, but yep, that's it. Now I wanted to go on to some things that have little complications in them. And something like that might be NO3 minus. So let's see, we've got 1 nitrogen and 3 oxygens. Oxygen, if you look at the list of electronegativities, you see that oxygen is the second most electronegative element of all, with only fluorine being greater. So nitrogen is definitely less electronegative than oxygen, and it's the unique element. So there's no doubt about it. In this case, the nitrogen goes in the center, and the oxygens are going to go around the outside. Okay, for the total number of valence electrons, we've got a nitrogen and we've got 3 oxygens. Nitrogen, group 5A, that means it has 5 valence electrons. Oxygen is group 6A, which means it has 6 valence electrons, but there are 3 of them. So that's 6 times 3. That's 18 plus 5 is, wait a minute, 6 times 3 is 18, plus 5 is, yeah, I almost forgot about the negative charge. Because I was going to say 23, wait, odd number? That's bizarre. Nope, it's because of the negative charge. That adds 1 electron to the structure and it ends up being 24. 24 electrons. We can start by connecting the oxygens with the nitrogen with single bonds. And so that's 6 electrons we've used so far. And now we can complete the octets on the outer atoms, keeping in mind that we're up to 6 electrons so far. So this is 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Okay, so we've used all the electrons. Cannot add any more electrons. And the last thing to do would be check for octets. If you'll notice, the oxygens all have octets because you've got 2, 4, 6, and then 2 more in the bond. That's 8. And the 3 oxygens are equivalent the way we've drawn this structure. So the other oxygens are going to come out the same. So oxygen's all set. All 3 of them are. What about the nitrogen? Well, nitrogen's got 2, 4, 6, and that's it. That's a problem. Because nitrogen also wants an octet. So the way that we can get an octet when we've used up all of our electrons and don't have any more to to add in is take one of the oxygens, and like I said, all of the oxygens are equivalent at this point. So it doesn't matter which oxygen you pick to do it, but take one of the oxygens and make it share one of its lone pairs with the nitrogen as a bonding pair. All right, so that lone pair is now gone from there, and it's now a bonding pair with the nitrogen. Nitrogen now has 2, 4, 6, 8 electrons around it. So nitrogen has an octet. The double bonded oxygen has 2, 4, 6, 8. That's an octet, so that's happy. The other 2 oxygens we didn't change, so they should still be happy. And so your Lewis structure for the nitrate ion should, whoops, forget that, look like that. When we draw the structure for an ion, we normally put it in brackets with the charge outside the brackets, just to remind ourselves that it's an ion. And so that would be the nitrate ion. For, say, another example, we can look at NCl3. In this case, yeah, I don't remember which is more electronegative. I think nitrogen is actually more electronegative than chlorine, but I could be wrong about that. They're close. Anyway, there's only one nitrogen though, so that goes in the middle. And the chlorines are going to be around the outside somewhere. For the valence electrons, we've got nitrogen, which has 5. And we've got chlorines, which have 7 each, but there are 3 of them. So that's 21 for them plus 5. That would be 26 total. We can start in with the electrons by connecting the nitrogen with the chlorines through single bonds, like so. Each single bond is 2 electrons, so we've used 6 so far. That means 20 more to go. So we've used 6, and now we need to fill in the lone pairs on the chlorines. So 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. We've only used 24 electrons so far, and we've filled the electron, or if we filled octets around all of the outer atoms. We've still got 2 more electrons to go. So it said, the rule said, at this point, if you have more electrons left over to go, you put them on the central atom as lone pairs. We've got 2 electrons to go. That's enough for 1 lone pair. So we put that on the central atom like so. And now we notice everybody has an octet. because that's what nitrogen needed to reach an octet, is 2 more electrons. And if we check the chlorines, we see 2, 4, 6, 8. And the other 2 chlorines are exactly the same, so they'll come out the same. And for the nitrogen, we have 2, 4, 6, 8. So everybody has octets. We've used all the electrons. There's our Lewis structure. So not too bad. We're at 30 minutes now, so I'm going to continue on with a couple more examples in part C in just a moment.